Hi, this is my video number 21. Right, so in this video I'll talk on the expansion of symmetric kernel in eigenfunction. Also give you some related theorem to it. Okay. So first let's talk on the expansion. Of symmetric kernel. In eigenfunction. Alright. So what actually we want to do is that from the given kernel K, we try to expand to find K2, K3, and so forth until you find K in general terms. So that's the purpose of what we are doing now. So first we let K xt, which is non-null or non-zero, and symmetric has finite eigenvalues, finite or infinite eigenvalues. So let's call this those eigenvalue has eigenvalues either finite or infinite. Lambda 1, lambda 2, and so on. We have lambda n plus 1, and so on. So, and we arrange such eigenvalue repeatedly. If there is a same eigenvalue, so we arrange in order. All right. So, and we assume that those phi we arrange in such a way that the absolute of eigenvalue lambda 1 has this kind of order, right? Lambda 1 less than lambda 2 less than equal lambda 2 less than equal lambda 3, and so on. Lambda n plus n, lambda n plus 1, and so on. So clearly from here, since lambda is positive, and lambda is positive, it's real. So we can see from that as n goes to infinity, this lambda n also goes to infinity. Okay, so now if we let the phi 1 x, phi 2 x, and so on, we have phi n x, phi n plus 1 x, and so on, as the sequence of eigenfunction. B is sequence of eigenfunction, corresponding to the given eigenvalues that we obtain here, corresponding to the eigenvalues that we have mentioned earlier, and then we arrange this eigenfunction in such a manner that they are not repeated. Yeah, they are not repeated. So means that if you have two same eigenvalues, eigenfunction, we just consider one. Okay, so we rearrange those things. So corresponding to each eigenvalues, eigenfunction, each eigenvalues, and we arrange the eigenfunction so that they are not repeated, and they are linear independence. Yeah, linear independence means we can write in terms of C1 phi 1 plus C2 phi 2 plus C3 phi 3 and so on equal to 0. That gives Ci is 0. So that's a linearly independent eigenfunction. So what happened then? It follows from those arrangement, or right? The each eigenvalue, yeah, each eigenvalue lambda k correspond to just one eigenfunction. Yeah? Correspond to just one eigenfunction phi k x, and we suppose that this eigenfunction has been autonomalized. So you know what autonomalized is. We have the norm of it is equal to 1, and the inner product between those two is if phi j equal to I equal to j, it gives you 1. I different than j, that gives you 0. So that the eigen are autonomalized. So autonomalized. So we have we suppose that as well phi k, each phi k, yes, suppose that the eigenvalues phi k x is or has been autonomalized. So I have explained in the my previous video that how to autonomalize the eigenfunction. Now let's suppose that a symmetric kernel has at least one eigenvalue. Yeah, let's suppose that a symmetric L2 kernel has at least one eigenvalue. So let's say this eigenvalue is lambda 1. Then from there we can find phi 1 as the corresponding eigenfunction, as the corresponding eigenfunction. Okay, and it follows that we can find the second truncated symmetric kernel. You can find the second truncated symmetric kernel. Let me use a new paper. Then the second truncated symmetric kernel can be written as K2 xt. This is equal to K xt minus phi 1x bar over lambda 1, where phi 1 is the eigenfunction correspond to eigenvalue lambda 1. So since lambda 1 and lambda 1 is non-zero, and k is also non-zero. So what we have basically, k2 is also non-zero. Yeah, so we have k2, this is also non-zero, or none now, I would say, none now, and possess at least one eigenvalue. Possess at least one eigenvalue. Let's say those eigenvalue lambda 2. In case we have more than one eigenvalue, we choose the smallest one. Yeah. In case we have more than one eigenvalue, we choose the smallest one. And then with the corresponding normalized eigenfunction, with corresponding normalized eigenfunction phi 2 x. Well, in this case, we can show that phi 1 x is different than phi 2 x. Yeah, even if phi 1 equal to lambda 1 equal to lambda 2. So you can show that by integrating those, yeah, k2, or the second truncated symmetric kernel, from limit a to b, integrate those things, k2 x2 xt phi 1 t dt. Yeah, this is from we multiply by phi 1 and then integrate from a to b. So what happened? We do the same here. So we got the right hand side is that a to b, yeah, k xt phi 1 t dt minus that one is we have, because this is we integrate with respect to t, so x we can take it out. So what we have is that phi 1 x over lambda 1, integrate from a to b, we have phi 1 t and phi 1 t bar dt. Alright, so from here, since we know that, yeah, since the homogeneous Freedom integral equation is given as phi 1 x, this is lambda 1 a to b k x t phi 1 t dt. So of course you can write this, or you can bring those lambda to the left side. So what we have then, phi 1 x over lambda 1, this is just a integrate a to b k x t phi 1 t dt. Then you can substitute in here, you got phi 1, that part here, and since our this is normalized autonomal eigenfunction, so that give you 1. Okay, that give you 1. So everything here, that give you phi 1 x over lambda 1 minus phi 1 x over lambda 1, that give you 0. Okay, so we can find also the third truncated symmetric kernel. We can find the third truncated symmetric kernel. Okay, given by k3xt equal to k2xt minus, we have phi 2x bar over lambda 2, where bar is the conjugate value of function phi 2, or of the eigenfunction phi 2. So, and here you can write this as a kxt, because kxt is given in the first part there, so you can write this as a xt minus, we have phi 1 x bar over phi 1, and minus those, minus phi 2x bar over lambda 2. Then you can simplify this, or we can write this in a more compact form. So we have, this is k xt minus, this is just the same, we change the subscript. Then we have this is the summation of, we can write k equal to 1 to 2, because we only have 2 here, phi kx phi k x bar over lambda k. So this gives the third eigenvalue corresponding to normalized eigenfunction phi 3. Alright, so if we proceed this, we will arrive at the following possibilities. That number one, we have k xt is summation of k equal to 1 to n phi k x bar over lambda k. Okay, because we proceed this until you have the up to n step, kn plus 1 is equal to 0. So what left, from here you can say that you have k2 that give you 0, and then k3 and so on and so forth. Then you can proceed up to n plus 1, that kn plus 1 that give you 0. So what left is that from here, since that part is 0, what we have k is equal to those things. Alright, so we have k, and up to n terms we have k equal to those. And number 2, that this process can be continued indefinitely, and there are infinite number of eigenvalues and eigenfunction. There are infinite number, there are infinite numbers of eigenvalue and eigenfunction, So this is the way how do we generate or expand the symmetric kernel from K, the given kernel, from the given Fredholm integral equation. We have the kernel. From that kernel, we can expand it to find K2, K3, and so on up to Kn plus 1 and so on. And later on, we can write that this K is actually the summation of the eigenfunction. Summation of the multiplication of eigenfunction with its conjugate divided by the eigenvalue. Okay, now let me just mention the couple of theorem. First theorem is that So if the Fourier series of the symmetric kernel, if the Fourier series of a symmetric kernel converge uniformly with regard to each of the variable with regard to each of the variable then its sum is almost everywhere equal to the kernel. Sum is almost everywhere equal to its kernel. So that's what we have discussed earlier. So we have k xt is equal to summation of n equal to 1 to infinity phi n x phi n bar over lambda n. So that's our first theorem. For this next, the second theorem, that if phi n is autonomous system of all eigenfunction, if phi n x is an autonomous system of all eigenfunction of a symmetric kernel of a symmetric kernel kxt corresponding to the eigenvalue lambda n, corresponding to the Alhamdulillah. Sorry about that. Alhamdulillah. Corresponding to the eigenvalues lambda n, then the symmetric kernel, pxt, this is also a kernel, symmetric kernel, equal to kxt minus summation of phi nx bar over lambda n from 1 to infinity, has eigenvalues lambda m plus 1, lambda m plus 2, and so on, where m is any positive integer. M positive integer. No. Okay, and then I have one more theorem or two more theorem that I want to share with you today. The next theorem is that theorem number 3, what we call as Mercer's theorem, MERCERS, Mercer's theorem. So if K is positive definite, if the kernel K xt is a positive definite continuous kernel, is a positive definite continuous kernel with autonomous eigenfunction with autonomous eigenfunction phi k, then this series phi n x bar over lambda n for n from 1 to infinity, this converge to k xt absolute and uniform. Absolute and uniform. So what that means, if our kernel K is positive definite continuous kernel with autonomous eigenfunction, you know what autonomous eigenfunction I've explained earlier and also in the previous lecture as well, autonomous eigenfunction, then those series converge to the kernel K absolutely and uniformly. Okay, and then the last theorem that I want to share today is that what we call as Hilbert-Smith's theorem. Theorem number 4. So let's call this as this is Hilbert-Smith theorem. So it says that if a function f(x), if a function f(x) can be written in the form, f(x) equal to integrate a to b k xt ht dt. I think you recognize this kind of a function where kxt is symmetric kernel and ht is L2 function, then fx can be expanded, then fx can be expanded in an absolutely and uniformly converge and uniformly convergence Fourier series with respect to autonomous system autonomous system of eigenfunction. We have phi1 x, phi2 x, and phi n x of the kernel in the following way. Yeah, of the kernel k xt in the following way. Which is fx can be written as summation of phi n fn phi n x n from 1 to infinity, where phi n is the corresponding autonomous eigenfunction, where fn we call it as a Fourier coefficient, where fn is Fourier coefficient of function fx with respect to the system, with respect to the system phi n x. That is, we can write fn is equal to the inner product of function f and phi n, which is the definition of inner product. We have a to b fx phi n x dx bar. This is the definition of the Fourier coefficient. So moreover, the Fourier coefficient fn of function fx are related to the Fourier coefficient hn of h by the relation, and we have the relation between fn and hn. Fn is given as hn over lambda n, where hn is the inner product of h and phi n. Okay, so this hn, if you look at from the beginning of the Hilbert-Smith theorem, we have fx is defined as the integration of the kernel and the function h here, and this h refer to that, this h here, and then we can find what this hn, where the hn is the Fourier coefficient of the function f, of the function h. Okay, so up to now, basically what we have done, from the given Freedom integral equation, we can expand the symmetric kernel in terms of its eigenfunction. Yeah, we can expand the symmetric kernel in terms of its eigenfunction. We have a summation of eigenfunction multiplied by the same eigenfunction conjugate of those, divided by the corresponding eigenvalue. All right. Next, we look at the solution of the Freedom integral equation of the first kind with continuous, real, and symmetric kernel. So we look at the solution of Freedom integral equation of the first kind with, it's not really well focused, just all right, with continuous real and symmetric kernel. Yeah, continuous real and symmetric kernel. So what we want to see here is that we're going to analyze what is the solution of the Freedom integral equation. Yeah. So we consider the the homogeneous Freedom integral equation. Yeah, we consider the Freedom integral equation, homogeneous Freedom integral equation, given as fx equal to integrate a to b k xt phi t dt, and with k, the kernel k xt is continuous, real, and symmetric. So the equation, this equation, let me call this equation number 1. I give a name. So this equation number 1 has no continuous solution. Yeah, this has no continuous solution unless fx is continuous, is expressed as a linear combination of the eigenfunction, yeah, corresponding to the associated homogeneous Freedom integral equation of the second kind given. So we have the corresponding eigenfunction fx is lambda a to b kxt phi t dt. Yeah, this again, let me express that again. This equation has no continuous solution. Yeah, this equation has no continuous solution unless the function fx is expressed as a linear combination of the eigenfunction corresponding to the associated homogeneous Freedom integral equation of the second kind, which is that. Okay, now let us assume that this equation has continuous solution. So let's assume that 1 has a continuous solution. Continuous solution. Then fx can be expanded in a series fx is equal to sum of fn gn x for x between a and b. Now how do we do this? Using the Hilbert-Smuts theorem that we mentioned earlier, where fn in this case is that fn is the Fourier coefficient, which is the inner product between fx and g and x. Yeah, this is integrate a to b, the inner product of function fx and g and x dx for all n, 1, 2, 3, and so on. And g and x are the eigenfunction, so let's call this 2, and g and x are the eigenfunction of 2 corresponding to eigenvalues lambda n, yeah, corresponding to eigenvalues eigenvalues lambda n. That is to say that gnx is lambda integrate lambda n integrate a to b k xt gnt dt. Okay, so let's call this that's equation 1, 2. Let's call this equation number 3, and let's call this equation number 4. All right. So from 1, 3, and 4, yeah, from 1, 3, and 4, we have integrate a to b k xt phi t dt. Yeah, if you look at this right hand side of 1, that's k phi, integrate k phi, which is f. Our f is given here. Alright, and then our gn is given here. So what you have, you can combine all those things, then this gives you summation of n equal to 1 to infinity. We have phi n fn integrate a to b kxt gnt dt. Or you can simplify this or rewrite those things that give you rewrite this, that's equal to integrate from a to b k xt. You have phi t minus, that you bring it to the left, summation n equal to 1 to infinity. We have lambda n fn gnt dt. Right, this is equal to 0. And basically this is all those things as we consider. If you consider those as phi t, then we have, if you consider that at phi t, then we have integrate a to b kxt phi t dt that equal to 0. Okay, now since equation number 1 here has continuous solution, yeah, which must be in the form of that equation. Yeah, that equation. So I need to write this thing. So where phi t is equal to psi t is equal to phi t minus phi n fn gnt. Yeah, n equal to 1 to infinity. So let me write those things. So let me give equation. This is equation number 4, number 4. This is number this is number 5. This is number 6. Okay, now since equation 1, yeah, since equation 1 contain continuous solution, yeah, because of it has a continuous solution, then we can write in that where is it? So we can write fx in terms of here, yeah, we can expand fx as that, because one has a continuous solution. So given one, since one contains the continuous solution, which is of that form, yeah, must be in the form of equation number 6 there. Therefore, we can say that from 5, either it satisfied by the trivial solution, satisfied by the trivial function phi x equal to 0, or it possesses infinitely many solutions, yeah, or it possesses infinitely many solutions. Now, if you multiply this equation number 5 here with g and x and integrate with respect to x from a to b, so yeah, we multiply 5 multiply by g and x, and then we integrate from a to b with respect to x. So what we have, integrate a to b, yeah, from 5 here, we have g and x, and then we integrate a to b k xt phi t dt dx, that give you 0. And since k is symmetric, so I can write that this is equal to integrate a to b phi. You can of course you can change the order of integration, so we have phi t those integrate a to b k xt, there should be tx here because t is symmetric, tx g and x dx dt. This is equal to 0. And using equation 4, that gn is given as this thing, all right, lambda n integrate a to b k gn t. So you can write here, this is just g, this is g and t from equation number 4. This is g and t, yeah, from 4. So what we have now is that 1 over lambda n integrate a to b phi t g and t dt, this equal to 0. So what we have there is that, so therefore this equation equation number 5 here, equation number 5 contain a non-trivial solution, yeah. So if this equation contains non-trivial solution, then that solution must be orthogonal. So this shows that the solution must be orthogonal to all the eigenfunction g and x. Yeah, so let me write those things. So if 5 contain a non-trivial solution, then that solution must be orthogonal orthogonal to all eigenfunction, to all eigenfunction, to all eigenfunction g and x, g and x. Okay, so let me repeat those phrases. If 5 contain non-trivial solution, so that solution must satisfy or must orthogonal to the eigenfunction Gn. So this equation here, this shows that the solution is orthogonal. Yeah, as you can see from there, you can see from here, the solution is given as because the phi is unknown. If you can solve this, means you can find what phi is, which is the solution is given by that. Okay, and this phi satisfy the orthogonality between phi and g. So if further you can have if a set of function is finite, then there exists infinitely many linearly independent function, and if the function Gn possesses an infinite complete set, then no continuous non-trivial solution can be simultaneously orthogonal to all function, yeah, of the set. Hence, in this case, the function is the function phi x is trivial, which is equal to 0. So I think I stop here for this video. So let me conclude what I have explained or what I have given in this video. That the first thing is, how can we expand the symmetric kernel in eigenfunction? We have a couple of steps that we need to follow. It's not really difficult. You just follow all those steps, and then we can also, using the Hilbert-Smith theorem, we can expand the function fx itself. Yeah, using the as a sum of Fourier coefficient multiplied by the eigenfunction for the corresponding eigenvalue, of course. All right, and then lastly, we have shown that the solution of the Freedom integral equation, continuous solution of the Freedom integral equation, then satisfy the orthogonality relation with the eigenfunction. Okay, so with that, I stop here for this video, then we continue with the next. Thank you, bye.